All right. So yesterday I introduced to you the principle of mathematical induction. It's a hugely important tool for proving things in mathematics. And so, it's inductive as opposed to deductive. So instead of, further specifying to a narrower thing, we're saying something very general. We're saying something that's true for all positive integers by starting with just a couple statements. And it is a proof. It's not just like a made-up hand-wavy thing, and see if you can understand how it's a proof. So just to review, you can say a statement's true for all positive integers n if first you show it's true for n equals 1. Check. So you've actually verified, yes, true for n equals 1. And then if you can, assume it's true for k, for n equals k, which could be any number. And if you can work from that assumption to prove it's true for n equals k plus 1, then you've proven it for all n. And the reason that works is because the integers, 1, 2, 3, 4, 5, all those numbers, the integers are all spaced evenly. All have a spacing of 1 between them. To get from 1 to 2, you just add 1. To get from 2 to 3, you just add 1. So then since you've proven it for 1, let's see. Since you've proven it for 1, that's the base case, then you say, well, you've also proven if true for k, then true for k plus 1. So then if true for 1, which it is, then it's true for 2. Oh, well now it is true for 2. So now if it's true for 2, then it's true for 3. And if it's true for 3, then it's true for 4. And for 4, then for 5. You see how you've got them all then. The proof of all proofs. So it's ingenious, really. Like it's a way to rope in all of the positive integers in one fell swoop. So boom, got them all, just like that. So it's pretty nice. So we were trying to go through the proof yesterday, and for those of you who are in the classroom, you can see it on the board where we left off. For those of you who are not, I think I have it here. This is kind of what we were getting at yesterday. The base case is simple. You just plug in 1 to this formula for j squared. So from 1 to 1, you plug in j equals 1, you get 1 squared, that is 1. Okay, well then plug it into the formula that we think is true, which is, we think this formula is true. So you plug 1 in there. 1 times 2 times 3 over 6 is 1. So that's the base case. Check. It is true for 1. And then we assume it's true for j equals 1 to k. And if it is, that means you can simply plug in k to the formula. And that's what you see here. It's just the same formula, right? It's just the same formula, but we're plugging in k. We're assuming that you can do that. And then we realize, okay, well, that's what we're assuming. What we need to show from that is we need to show, this is what we need to show. We need to show that this piece from 1 to k plus 1 equals just plugging k plus 1 into it all. That's the idea. So I just plugged in k plus 1 to the formula wherever there was an n. So wherever there was an n, I put a k plus 1. And so what you see down here is just all the algebra to distribute it and get, okay, so that's what we got to show. We got to show that you can go from the summation 1 to k plus 1 and get to this simple fraction. That's where we were. Okay, so I'm going to show the steps from here on again, just to help. Okay, so we're trying to show, I'll copy and paste it so we can take it with us. This is what we need to show. That's what we need to show. Okay. Well, let's see what we can do. So if we consider the sum from j equals 1 to k of j squared, k plus 1 of j squared, well, that just means the sum of the first k plus 1 squares. You can imagine going up to k squared, and then to k plus 1 squared would be the last term. So it's just adding up all those squares. Anyone have an issue with that? Okay, and then, then you see that here, that piece is actually the sum from 1 to k of j squared. The first k terms are that sum, which we already assumed, we already assumed that that was equal to, I'll write it here, we assumed that the sum from j equals 1 to k of j squared is equal to k times k plus 1 times 2k plus 1 over 6. Well, then that means we can substitute that in. So now we can say that, okay, the sum from j equals 1 to k plus 1 of j squared equals this piece here, k times k plus 1, 2k plus 1 over 6. And then, so all that plus this piece, that k plus 1 squared. So I just made a substitution. Any issues? All right. So now keep in mind, we said we need to show this thing right here, highlighted up top in the right, and that thing's all one fraction. So right now we don't have one fraction, so let's try to get one fraction and see if we can get it to look like that. So, okay, one fraction, that means we should multiply this by 6 over 6. And so then that's just equal to k times k plus 1 times 2k plus 1 plus 6k plus 1 squared over 6. Okay, and I noticed looking at those terms that here's a k plus 1, and here's a k plus 1 squared, so I can take a k plus 1 out. So let's do it. So that's equal to k plus 1 times k times 2k plus 1 plus 6k plus 1. There's just one k plus 1 left over there. So still not exactly what we're not exactly finished. Doesn't look like what we're trying to show yet. So the most logical thing I can think to do would be to say, well, you have this kind of weird term that's got some addition in it. Let's try and distribute pieces of it and then factor it once those are redistributed. So let's distribute what's inside those brackets. That'd be 2k k squared plus k plus 6k, so that's plus 7k plus 6 over 6. And then now that quadratic term, the 2k squared plus 7k plus 6, we think through it and we say, well, that's got a factor, let's see, 2k something, k times something. In fact, if you do 3 here, wait, nope. What is it? Oh, sorry. Other way. Yeah. Plus 3, plus 2. Yeah. So that gives you the 2k squared plus 4k plus 3k, which is 7k plus 6 over 6. And if you look, that's what we were trying to show. Right? That was this piece. So we did it! Whoa! So then how do you wrap this up? Yeah, that's what we need to put at the end. So this is how you would say it. You'd say something like this, which is what we were trying to show. Thus, now you can make your final statement. And maybe you'd even add something like this. Thus, by induction, the sum from j equals 1 to n of j squared does in fact equal n times n plus 1 times 2n plus 1 over 6. QED. Rejoice. Simple as that. Okay, now that you've seen it in full, are there any lingering questions, doubts, concerns? Yes, Parker.
We're going to have to do this process every time we have a problem like this.
Mm-hmm. That's why you wouldn't have very many of these kinds of problems. They take a little while, you know? Can you see the logic of the proof? It's pretty amazing, right? Oh, I guess I could also say this. Thus by induction, this equals this for all positive integers n. Because that's you can't just plug in 1.5, you know what I mean? Or negative 6. It's got to be only positive integers.
Well, now that we have this proof, why do we need to do this?
Well, there's so many more things to prove, Ian.
We're only scratching the surface.
But do we have to prove something like this on the test?
Yes.
Would we have a practice problem in the review packet?
Perhaps, yes. So let me give you this one to try. I'd like you to do this one. You try. Prove this statement. Prove that the sum of the first integers, just not squares, just 1 plus 2 plus 3 plus 4 plus 5, the first n of those numbers equals n times n plus 1 over 2. This is pretty nice. I mean, if you want to start doing, you want to help your siblings, brothers, sisters with addition and stuff, you can just do a bunch in your head real quick. Oh, you want to add up the first 10 integers from 1 to 10? Okay, it's just 10 times 11 over 2. 55. Boom. Got it. You're so fast. You'll freak everyone out. How does he do it? How does she do it? And so you can see that this is true. So if you did, my pen's dying here. So 1 plus 2 equals 3. So you can see that, okay, 2 times 2 plus 1 over 2 is in fact 3. The formula checks out. 1 plus 2 plus 3, well, that's 6. And in fact, 3 times 4 over 2 does equal 6. So I'm just showing you for the first few that it does work. But we want to know that it's true for all n. Alright, so I just gave it to you for the first 5, really. I mean, I skipped 1, but hopefully you can see that 1 equals 1. 1 equals 1 times 2 over 2. Okay, so just remember you got to do the couple of steps. So you got to go through the base case, show that it's true for n equals 1, and then assume it's true for k, prove it's true for k plus 1. All right, and if you're watching on YouTube, please pause the video and try it yourself. All right, so let's just look through the whole thing so we see it all together. So we're trying to prove this statement here, so the proof. Okay, so we first show the base case. That looks like a D. First, the base case. That is, when n equals 1, the sum from j equals 1 to 1 of j equals 1. The first 1 integers is 1. And then if you plug in 1 to the formula, 1 times 1 plus 1 over 2 does in fact equal 1. Nothing crazy. It's true when n equals 1. Now, the harder part. Assume it's true from 1 to k. Assume it's true from 1 to k. So that means that sum would equal k times k plus 1 over 2. You assume that, and you say we need to show from that, we need to show that the sum from 1 to k plus 1 of j equals, and then substitute in k plus 1 wherever there was k's before. So it would be k plus 1 times k plus 1 plus 1, or just k plus 2 over 2. Issues there? Objections? All right. So we have the base case. We know we've assumed what we're assuming. We need to show this now. So then let's do it. Let's say, okay, from 1 to k plus 1 of j, let's just start writing it out. That's 1 plus 2 plus 3 plus blah, 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 all the way up to k plus k plus 1. That's just the expanded form of that sum. And if you look, you can see that these first k terms are in fact this. Or sorry, not that. They are this. The first k terms are that sum. It's the sum from j equals 1 to k of j. That means, since we assumed that that sum equals this, we can now substitute it. So let's substitute it. So k times k plus 1 over 2 plus k plus 1. So we made our substitution. And now it's just as simple as, let's see if we can make it look like what we need it to look like. So let's get a common denominator, 2 over 2, and this becomes k times k plus 1 plus 2 times k plus 1. And actually I wouldn't distribute here, I would just factor. And so you factor out a k plus 1, that leaves you with a k plus 2 over 2. Oh wow, that's what you were trying to show. So you did it, at this point, there you have it. So any questions through there? So I'll say, which is what we were trying to show. So thus, by induction, the sum from j equals 1 to n of j does in fact equal n times n plus 1 over 2 for all positive integers n, q, e, d, just like that. So now it's true. It's true for, I mean, it was true, but now you know it's true. Hopefully. Okay. Any questions? Oops. All right. So I wanted to just look at one of your homework problems to help you get a head start on one of them. Because I talked with some students that are having some issues with it, so I wanted to see if I can give you some help. If you have your book, it's on page 524. It's number 2 on page 524. It's one of your homework problems.
What page is it?
524. Okay, so you're trying to show that this statement is true for all positive integers n. So I just want to help you see the setup of the problem. It's the same kind of thing as what we've been doing, but it's the sum is given in expanded form instead of in sigma notation. So maybe for you it would be helpful to get it in sigma notation. So let's think about this. This is the first term of the sequence, second, third. This is the what term? What's that? Nth, yeah, nth term. So there's n separate things being added together. So make sure there's all those different pieces being added together, n of them. And what the claim is that all of those things can be added. You can get that number by just taking n over 3n plus 1. That's the claim. So it might help you if you could see how to write this left part in sigma notation. So let's say we're going to go from j equals 1 to n. So we need a formula with j's in it that eventually could have n's plugged into it. So I'm going to have a fraction. What goes on top of my fraction? 1. And on the bottom?
It's just. Is it 3n minus 2 and 3n plus 1?
You're close. Think about this, Parker. N, which you see over here, that's for the nth term. And so when we get there at the end of our sum, we will plug in n. And we need to get that.
Is it 3j minus 2 and 3j plus 1?
Exactly. Yep. And you can test it just to make sure, convince yourself. If you plug in 1, does it give you the first term? So 1 over 3 minus 2 times 1 over 3 plus 1. Yes, that's 1 over 1 times 4. What if you plug in 2? So 6 minus 2 is 4. 6 plus 1 is 7. So it's looking like it actually does work. This is the formula for summation notation. So then what you're trying to show then, the whole goal of this problem is to prove that that equals this. That's what the problem is asking you to do.
So when you're doing the primary term, do you use the n3n plus 1? Or do you use the 1 over 3j minus 2 times 3j plus 1?
So the 3j minus 2, 3j plus 1, that's how you get each term of the sum. Like each little, like if the sum, like if you're adding together all the pieces of a pie, this is each piece of the pie. Right? But the n over 3n plus 1, that's the whole pie. Right? That's all the pieces put together. It's supposed to be n over 3n plus 1.
So then, is that the one that you use to solve for the primary, and then you just add, or substitute k plus 1 for the n's, and then n over 3n plus 1?
So by primary, do you mean the base case?
Yeah.
Oh, like the first part of the proof?
Mm-hmm.
So for the first part of the proof, you say, what's the sum of the first term? So you know, what's the sum from j equals 1 to 1 of 1 over 3j minus 2, 3j plus 1? How did I get that? Plug in 1 for j. So that's 1 over 3 minus 2 over 3 plus 1. And that is 1 over 4. So you plugged 1 into the sum formula, and then let's plug 1 into what, that's 1 for the term of the sum. What about this part? So then you plug in 1 there. 1 over 3 times 1 plus 1 does in fact also equal 1/4. So there's the base case. You've shown it's true for n equals 1.
Are we going to have any of them that aren't true?
No. Only true things. Okay, so I hope that, I know some people I was talking to, they got kind of stuck and couldn't even see what they were trying to prove, so hope that's a helpful boost for you there. In case you don't have the homework exercises written down, they're right here. It's those problems. And that will be